you. So I want to show you some of the results that we achieved last year with the project in DroneSOM, with test sites. Oh, the wrong side. With test sites in Finland. So first, the DroneSOM project, which I present the results today, are from a Kava 8 upscaling project co-funded by the EIT RawMaterials, and this is a project to bring prototypes towards the market. And together with our partners like the GTK from Finland, Radai from Finland, and the Technical University of Denmark, we had basically two different goals in this project, or two different steps, but the overall goal of this project was to create a service that combines the fast and cost-effective geophysical data collection with data modeling and integration. And it consists of basically two parts. The first is the upscaling of the drone geophysical measurements for electromagnetics with Radai, and gravimetry measurements together with the DTU. And our part was in the second part, the upscaling of the interpretation and integration technology, where the GTK developed their 3D inversion of EM data further. And we at Beak developed our advangeo software further for 3D integration with the method self-organizing maps for 3D data. So the self-organizing maps, on the next slide, I will show you a video how this works. It's basically a clustering method where you first transfer your data, your different input layers that you have here are mapped to another space in SOM, which is much smaller than this geospace. And there you do another k-means clustering and bring it back to this geospace. And here's the video that hopefully works. Ja, da war's.
Nee.
Nicht das?
Weil der Mauszeiger verstellt ist. Muss man den Mauszeiger zu. Ich müsste mich von da aussetzt.
Okay.
Self-organizing maps, SOM, is a machine learning method that can be used in geosciences for integrating data, for example, to aid in exploration targeting. Here we have a good amount of pre-processed geospatial data collected with different methods, such as geophysical surveys. Creating a SOM means rearranging the data points from the pre-processed data map to new maps. Imagine taking the data points from all of the original maps, throwing them in the air, and letting them land in a new place, now sorted by their similar properties, such as magnetic anomalies. That new place is called a SOM space, a smaller map where similar data stick together. SOM nodes can be further clustered to divide the data into a handful of groups that are internally homogeneous and different from each other. After clustering in SOM space, we place the results back onto the original map. Now, all the different data maps are integrated into one cluster map, showing clear groups and patterns and making hidden structures in the landscape visible at a glance. Checking where the known occurrences fall on SOM, prospective clusters can be detected and then evaluated further. The solution opens up entirely new possibilities, for example, in mineral exploration within the target area.
So this video explains applying the SOM to a 2D data, but what we did here in this project is applying it to 3D data, so 3D volumetric data. Our first test site was using data from the SEAM-STEEP project, and this SEAM-STEEP project did geophysical surveys at the Koillismaa layered intrusion complex in northeastern Finland, where they have no nickel, cobalt, vanadium, and PGE potential. And the data available in these projects or geophysical surveys they have done were 2D and 3D seismics, collected source electromagnetics and magnetotellurics, and resistivity tomography or induced polarization. And we had some additional data from GTK provided for density and magnetic susceptibility. And all this data, very important step for 3D data. First, you need to derive 3D data for geophysics, and how you do that is doing 3D inversion to your measured geophysical data sets. That means For electromagnetic data, for instance, when you do a 3D inversion, you get 3D volumetric conductivities of the subsurface. And for gravimetry, this means you get the densities of the subsurface, and the magnetics, it means you get magnetic susceptibilities of the subsurface. Yeah, and for seismic data, you usually do 3D seismic tomography to get the velocities, the seismic wave velocities of the subsurface that can be used for the data integration. And here on the right side, you see some examples of these data sets that were prepared. So you always see of this cube 2 slices, and in addition, some volumetric representation of the highest anomalies of this data, resistivity, magnetic susceptibility, density, and here the seismic velocities. And then in the SOM, multiple geophysical models are combined, the ones that I have just told. This SOM then generates a map for each of these 3D input parameter, as you see them here. So these are the SOM parameter maps, which on a much smaller space, so the data is reduced. And now you see how you get this 3D data onto a 2D map. So you have lots of points from the 3D space clustered in one SOM node. Then the SOM can generate the cluster map, the k-means clustering, and inside of one cluster, then you have all the points from the 3D space that are similar to each other in their data parameters. And these clusters then can be further evaluated using this hit count map. So you see how many points from the 3D space are mapped into one SOM node. So here in this example, it's more than 8,000 maximum. You can use this U-matrix plot, which shows the difference to their neighbors in the parameters. So it actually shows you the borders of your clusters, and it gives you a hint if the amount of clusters that you have used here is good. And the box plots you can also use, so you get one of these plots for each of your parameter, and it shows you the data distribution within your clusters. So in the next step then, or the last step, these clusters here are mapped back to the 3D geospace, and they can be visualized then in 3D to model exploration targeting. So as you see here, these clusters mainly reflect the geology in 3D of the subsurface. You have like the banded iron formation that shows up here, and you have some mafic and ultramafic intrusions. Then the second test site where actually our partner Radai flew with its drone to collect electromagnetic and magnetic data there. This was in Kupuka. So there you have Kupuka flake graphite deposits in, let's say, central Finland. And on the right side here, you see a map of a pre-existing magnetic anomalies, together with the areas of interest and some drill holes that were drilled there. And down here, this is in this box, this is the area of interest that we were focusing on. And this is the data that was acquired by Radai with the drone. So the magnetic data on the left side, and on the right side, which the map is not so easy to show you the EM data because it has 3 components, and it has always an in-phase and a quadrature part. So here it's really difficult to say where's the anomaly and how you can evaluate it and so on. And here in the center, you just see a model that was provided by Kupuka that they have built for the solids that are of importance to their exploration. So this is now this processed 3D input data that we used. So on the left side is the magnetic susceptibility, so the total component with its histograms down here. On the right side, you have from the EM measurements, the set components for the resistivity. But since we are looking for graphite, we are most interested in the highest magnetic anomalies and the highest conductivity anomalies. So here we have resistivity, but the inverse of resistivity is then the conductivity. So another processing step that was applied here is first cutting all the very high resistivities to use only low resistivity, which is high conductivity, apply an inverse scaling, and then exponential scaling to bring up the highest conductivities more, to pronounce them more, and in the end, finally, again, a linear scaling, because what we want to do is getting all the input layers to the same range of data, which is usually between 0 and 1, so that they are comparable to each other. So finally, this was then the data that was used as input, and here you see the results. So the magnetic susceptibility, and then here the conductivity, so only the highest conductivities anomalies here, and then the parameter maps in SOM. And here we can really see where are our highest magnetic anomalies and where are our highest conductivity anomalies. And then we can identify also the clusters that are in the same space. And the ones of interest are these cluster number 8, 9, 12, and 14. And actually just this cluster number 8 is the one with the maximum in conductivity and magnetic susceptibility, so the one of highest interest. And this is what is shown here in this volumetric representation on the right side, together with, again, 3 slices through this cube. And on the next slide, and my last slide, I just applied different colors to the clusters. And here you see the 3 clusters that are of interest: maximum conductivity and magnetic susceptibility. And together with the cluster number 9 for the maximum in magnetization, and 14 maximum in conductivity. And altogether, you see them here on the right side. But just cluster number 8 is the one of most interest. And now this model is then provided to the customer back again, and he has his drill course, and he can compare it now and evaluate it further with the drillings and the locations where they found or where they hit the graphite. So this is it. I'm happy to answer your questions if you have some. And thank you for your attention.